Hi, this is Dr. Tagwa, the Chair of Computer Science Department at the University of Nevada, Las Vegas.
Hi everyone, I'm Dr. Fonseca.
I'm Ben Cisneros.
And I would like to invite you to watch
Building Wikipedia N-Gram Corpus. So I am going to talk to you about what an N-Gram Corpus is, why we chose Wikipedia, how we actually got the data from Wikipedia via an XML dump, and building the 1 to 5 gram corpus dataset. And then we're gonna take a look at two ways of doing that. And then I'll do a quick analysis of the data set and then tell you what is on our plan for the future. N-Gram data sets are words that are one after the other and they form phrases that are used in the regular English language. And those are very useful for being able to do error correction with NLP. So when you're trying to correct an OCR error or a human error. They can also be useful for word prediction, like when you're typing something on search engine, and to also correct those kind of errors as well. It can also be very useful for training data whenever you're trying to do some sort of natural language processing. It can also be useful to do data analytics on articles and things like that, since this is coming from Wikipedia. Now, an example of a data set that already exists like that is Google Web 1T corpus. This data set goes from 1 gram to 5 gram. The gram number represents the number of words in the phrase. So a 1 gram or unigram would be a dictionary essentially, and a 5 gram would be a 5-word phrase. The example that we see on the top here is actually a 3 gram because there's 3 words. As you can see, the way that they're set up is you got the word 1, word 2, word 3, and the frequency of the time that it appears. Google Web 1T corpus dataset is very popular. It's about 20 gigabytes of uncompressed text files, and there's about 13.5 million words in the dictionary. That's a unigram, and then about almost 1 billion trigrams. However, anything with a frequency of, I believe, less than 20 is removed from this dataset to keep the size of it low, which is something we don't do because it could be useful to have something different. So why did we choose Wikipedia? Well, there's about 40 million articles, of which 6 million are in English, and Wikipedia is one of the most visited sites in the world, and it's constantly growing, and it's always getting new data about recent events and new terms that could appear in the English lexicon. So it's a constantly updated representation of the English language versus Google Web 1T, which was created several years ago now and is a snapshot in time. Modern phrases or even memes would not appear there. And so how do we get Wikipedia and turn it into an N-Gram data set? Well, the first thing we do is we go ahead and download the XML dumps. Wikipedia backs up its database at least once a month, but sometimes more often. And what it is, it's the entire website in one big file that's about 17 gigs compressed. And once you extract it, it's about 75 gigabytes. And it's free and publicly available. And then the next step we do is we use Wiki Extractor. Giuseppe Attardi and Antonio Fuscetto. This is the link to their GitHub on it. What it does is it turns the XML file into individual article text files, and it removes any other things because the XML dataset is downloading the website, and there's tons of extra stuff there that we don't need because we're looking just for the raw text and removing anything else, HTML or links or things like that. We're trying to get rid of all of that. So Wiki Extractor does a very good job at that. So why reinvent the wheel? It took for Wikipedia in our computer about 106 minutes to run. After that, we separate the data into 1 megabyte files, and we convert any special characters like numbers or mixture of numbers and letters or special symbols into tokens that are like num and anum. And these become very common once we generate the n-grams. And the number, which means numbers in our data set, was the 5th most common token with 63 million instances, which is to be expected because numbers are very popular. When you're reading something or when you're talking, you use numbers very often. And the reason why it's a good thing to combine is because when it talks about context-based, if we have something in the form of born in 1990, it's better to say born in num, because if we say born in 1990 or born in 1983, both of those mean the same idea of some sort of birth date. And so when you're doing natural language processing, this is a very useful concept. And so this process of sanitizing took an additional 2 hours and 41 minutes. From there, we have 2 ways of generating the n-grams. I'm going to talk about one of them, and I'm going to hand it over to Ben to talk about the other one. One of the things we tried and actually didn't work out well was we tried to just insert it into a SQL database. And the insertion was taking about 1 day for every 100 megabytes, and that was extremely slow considering the size of the data we have. So what we ended up doing was trying to simplify everything as low as possible to just sort and write and read from files and basically calling Python sort functions. And we were able to generate the 1 to 5 grams in about 30 hours, but we required about 500 gigabytes of RAM, which we had to use a special computer for. Once we did that, the size of the data was actually 95 gigabytes compared to Google Web 1T's 20 gigabytes, of which in the unigrams we had about 70 megabytes in size and about 6 million unique unigrams versus Google's 13 million for Google Web 1T. And now I'm going to go ahead and hand it over to Ben so that he can talk about the other method that we did.
So the whole idea about using trees was that we wanted to implement an adaptive approach where the memory cost of a regular trie is reduced by adapting the data structure used for each node to a number of children that it needs to store as opposed to how many it may have. And we did this by implementing two data structures. We ended up using a hash table and a combination of an array with a red-black tree. Let us talk about trie data structures. Instead of using the entire value of a key to find a place in the tree structure, like for example, a binary search tree where you will normally compare the whole key to the current node. With a trie, what we normally do is we break down a key into a sequence of characters, and then we make a node per character as you go down the tree. The downside with this is that in this particular example, there is a lot of wasted space for each node. If you look at every single black bolded letter, those are 9 nodes that we have in this current tree. And since we're talking about the English language, which has 26 letters or characters in the alphabet, now if we were to multiply the 9 times 26, that will give us roughly 234 pointers that we're using or supposedly using. But then if we subtract those 234 minus 9, we'll end up getting roughly 225, which is out of the 100% of capacity that we could use, we're only using a total of 4% out of 96%, which represent exactly how much space we are completely wasting, because all the other letters which behave as pointers are no longer being used, just for this particular example. So here, this is basically the adaptive approach that we have. The most significant changes that you can see here are, for one, we have the adaptive node structure as well as the adaptive structure attached to each leaf node. So first, we change the data structure used for each internal node, which now depends on how many children the node actually has. So we went from having 26 pointers to simply just having only one. We no longer use an array, but instead we use the hash table, where as the key we have just a single letter, and as the value that will be a pointer to the next node as we branch out or walk down the tree. The other thing that we have done is that we have attached an array that belongs to every single leaf node, and that array is a container for all the type of models that can represent an N-gram. The great thing about using this array is that it only grows depending on the type of N-grams a word is part of. So for example, Jorge mentioned about unigrams, which will be really rare, but if in this case you have only one single word, then the array will never grow except for just the word that it will contain as part of the leaf node. But the more words you keep adding, the more then it will grow. And every element inside that array will represent a red-black tree, where those nodes that belong to the tree, where the root represents the actual unigram, will be pointing to adjacent nodes that, if you put all them together, will form or create a sentence depending on the type of model that you're using or implementing. In the example that we see here, we have the node car, who represents the subtree being the root of a red-black tree, and then its children will be pointing to the next word in which it was found. Finally, the best way to think about this is as a combination of trees, where we have a linear character strings that represent the actual input, and you can think of that as a two-dimensional structure, because the two-dimensional structure comes from forming the red-black tree that is attached to each leaf node. The leaf nodes interior to the tree are the words in an N-gram. They are not only the entire input, but they also tell you how they were matched. And if you know how they're matched, you can know how to respond to them. If you look at figure 6, you could see that that triangle represents the red-black tree, where it only contains pointers to the nodes adjacent to that particular root node. They represent the information that we can use to quickly look for the words that are adjacent to some word that you're looking in particular, or how many words can be found in a Word document. For instance, assuming that you're using a trigram, if you want to know where the words that come before the word home, assuming that all of those 3 nodes are linked together because they were found in multiple sentences in a paragraph, and so then you can see how they're connected, so you could backtrack of the entire sentence. For the runtime, it was surprisingly very fast at the cost of memory usage. Unfortunately, we were not able to go beyond a trigram, and now I will give that back to Jorge.
Thank you, Ben. That concludes our presentation. In the upcomings, we want to improve the process by using MapReduce to either lower the amount of memory required or speed up the process. And we also are looking at ways of making this dataset available to other people so that they can run their own experiments and do their own data analysis, and ways of constantly updating it with the latest XML dumps. For further information about Google Web 1T, you can check out one of our papers. And I'd like to thank you all for looking at our presentation. I hope you have a great day. Thank you.
Thank you.
Thank you.